Today, I will be talking about the interplay of spectral efficiency, user density, and energy trade-offs in random access protocols. This is a work that I have presented in last year's YOP, and it has been extended, but today I will only discuss the infinite block length regime. The finite block length regime results can be found in the paper, which I hope I will upload soon as well. So the problem is motivated by understanding the fundamental limits of retransmission-based random access. So this is indeed, there is a bottleneck due to the overhead of scheduled access when we have multiple, a lot of number of users, especially in URLLC and IoT type of applications. And for these models, sequence design for individual users can be very difficult and not practical. Therefore, the goal is to design and analyze a retransmission-based protocol by exploiting where the power consumed by all the users can scale sublinearly with the number of users. And in this model, we want to combine the capabilities of NOMA-based transmissions with HARQ type of protocols in the receiver side that relies on chain combining or incremental redundancy to be able to combine retransmissions. And also, this approach will provide insights on how we can allocate the resources in the uplink direction for next generation wireless networks. So there is various related work in this direction that focus on random access models originated by Polyansky's work, even before Polyansky's work, sequence design, and also various access models that are originally designed before finite block length models came out. And then for the multiple access problem, interference management is a serious issue and resource sharing that has been also studied. And then with the advent of this HARQ-based models and new coding sequence design, this problem has been further explored. So there's a short list version of the references that I have been using in my work here. And here the general challenge is to design protocols for random access communication where we can maximize the scaling of the density of users that simultaneously access the channel with the SNR per bit. I will define this metric shortly. So here is the frame. Here is the model that we are thinking. It is a slotted model. On the y-axis, you see the different time slots. On the x-axis, we have the different frequency bins. So there are capital B bins in this model and capital T slots per frame. And in the time axis, we know that each user is allocated capital T transmit opportunities. And therefore, the total block length of the user is split among these transmit opportunities equally. So, and in this model, each user transmits over shared radio resources over to a common receiver. And the goal of each user is to transmit a fixed size payload, which is in L bits, within the latency constraint. And as I mentioned, the user is granted a capital T transmission attempt to be able to communicate this payload. And in this frame, we are assuming that the total allocated bandwidth is omega hertz, and it is evenly partitioned into capital B frequency bins, and each of them has equal width. And we have a duration of tau seconds. Again, it is partitioned into capital T time slots, so which is same as the number of transmit opportunities. And for a given frame, we can compute the number of resources, which is also equivalent to the real degrees of freedom we have in the system, which is nothing but the product of the bandwidth with the duration, which we denote by capital N. So this will be the real degrees of freedom. And this RDOF will be evenly split into capital T retransmissions. And each time frequency slot, which is nothing but one of the squares in the frame that you have seen, and it is given a frequency bin and time slot pair. And for given set of parameters, omega, tau, B, and T, we can compute the number of symbols in a TFS, which is nothing but N equal to omega tau divided by BT. If we assume that we share the resources in an orthogonal manner among all the users, we can compute the coding rate to be L times L divided by the small n bits per symbol. But this is not what we want to do in this work. So given the block length n, the block length per transmission is small m, which is given by the ratio of n and t. And there is a bit of notation in this work, so I was not able to avoid it. But this calligraphic JT is the set of active users for a given time slot t. And J is the set of all users in the entire frame. And this J, the letter J is sum of all these small J sub T's over all the time slots. And we have an encoding function for each user, J. J is the user index, and the user has a message size of K. And this is the original size of the message, which will be translated into N. So this is the encoding function that takes this K bits and transforms into this alphabet. And of course, this is done for each entry of the encoding, input of the encoding, and the output has size n for each transmission attempt. And this source vector has a dimension of k. And then the retransmission of the user j at any given time t is modeled by this capital XTJ vector. This is nothing but simply it can be represented as the product of its signature or spreading sequence S of j multiplied by some complex number a sub tj. And here the signature does not change from one time slot to another time slot. Each user has a fixed signature. And we assume that for any given time frequency resource block, the resources are shared in a non-orthogonal manner. So therefore, when I consider two users, J and J prime, when I consider the inner product of their signature sequences, it is not zero. It is defined, it is modeled by this parameter eta. And if I consider the inner product of the user J with itself, it is unit. So the parameter in front of S, that's the A sub Tj, models the power of the transmission. What we exploit in this work is a result by Polyansky. So in short, it is known as the KM construction, Katsurachian-Matri-Rossian construction. It enables us to be able to scale the number of users with the block length in the best possible way. Indeed, when the block length per transmission is small m, we are able to ensure with this construction, this eta, the non-orthogonality factor between the users, it scales approximately inversely with the square of the block length with high probability when the sequences are selected randomly. And again, as I said, the number of real degrees of freedom in this model is capital N for a given frame. So we can think that this to be the total length of all the signature sequences of the active users over this B frequency bins over for a given time slot. So just a visual explanation for this model. At any given time slot, for example, I indicate time slot 1 with the green color. I have a bunch of active users as shown on the left column, and each of these users has different signatures, and these are not orthogonal to each other. What we do is whenever this set of users are transmitting, their signals are being accumulated. And the signature of a user is not changing over different time slots. When I consider a different time slot T, for example, as you see in the middle, we will have another set of active users. And some of the users that were available in the previous time slots could be still transmitting in that particular time slots because each user has a capital T retransmission attempts. Okay, so this was an example for non-orthogonal user signatures. And the user in slot 1, as you can see in the middle of slot 1, is repeated in the T retransmission attempt. And each waveform at a given time slot will be the sum of all these non-orthogonal signatures. So when we look at the received signal at the receiver, what we assume is a classical additive channel model where all the retransmissions are added at the receiver, not only the desired signal to be coded by desired signal of user J, but also the other active users that are transmitting in the same time slot. And by using the definition of these XTs, we can rewrite this expression using the signature sequences of the transmissions. And here, this S sub T minus J is the set of interferers that are interfering with user J in the same time slot. And we assume that noise is complex Gaussian. And the receiver has to decode by combining the capital T retransmission attempts for the user from the received signal vector. And to do so, it combines all the received transmissions by using the standard maximal ratio combining technique, which is also being used in understanding the performance of chase combining and incremental redundancy techniques. So here, the received signal can be considered as a combination of all the retransmission attempts over this capital T time slot. And it can be written in this additive form. And here, when we do maximum ratio combining, what we need to do is we receive the signal, and then we need to multiply the received signal with the right vector to be able to decode with the highest SNR. And these are some technical details maybe we can discuss offline, because I believe I won't have enough time. So just to go into the details of the model, so we first consider chase combining of this HARQ-based, NOMA-based retransmissions, where each retransmission contains the same data and parity bits. From one transmission to another transmission, nothing is changing. We retransmit the same information. And at the receiver, the retransmitted packets will be summed with the previously received packets, and the buffer size is kept same. It is just summed, the received signal is just summed with the other retransmissions to be combined. And once the transmissions are added at the receiver uses maximal ratio combining prior to decoding. And it can be shown using this diagram, where the transmitter has capital T transmissions, and each of them are identical. And at the receiver, all the transmissions are added up together prior to decoder. And the buffer size of the receiver can be considered as the same length as the transmission per attempt of the user. Okay. So to be able to understand the scaling results between these different metrics, I first look at the per user received SNR. And of course, this model has limitations, like there are some idealistic assumptions. We assume that the total power of the channel input scales linearly with the message size. The original message size was K. And we assume that, so this expected value of this X vector multiplied by itself, it's the power of the signal transmitted. And here I assume that is equal to small m times sigma t square times rho tj, which is upper bounded by this expression. Let me quickly explain. So this m sigma square is nothing but the noise power across these frequency bins that the user is simultaneously using. And some additional simplifications to be able to achieve this upper bound. We assume that the signal has unit zero mean, and also this inequality is also satisfied for users that are different from each other. And also one term that I did not mention was this rho. Rho is the SNR. It's the SNR at the receiver when J is transmitting at time slot T. And when we want to compute the received SNR, it is going to be given by the ratio of this power of the signal received divided by the noise power. And if we simplify all the parameters, assuming that it is not changing from one slot to another, it can be given by using the magnitude square of the transmitted signal rescaled by the total noise power received over the bandwidth. And I also assume that the received SNR per user is also identical across different slots and different users. And the total power spent by all users can be computed by rescaling the power, which is nothing but SNR row multiplied by the noise power, and also the number of users. So one important metric that in our approach, what we want to understand is the spectral efficiency, which is nothing but what Shannon has calculated in bits per second per hertz, or bits per channel use, which is nothing but the total number of data bits per real degrees of freedom, which we use the subscript SE. And I also realized while listening to the previous talk, there might be some connections between my approach and your approach, and I would be happy to discuss the details. So similarly, this SNR per bit is another important metric in our approach, which is you might know this as EBNO. It is the ratio of the energy per bit divided by noise power spectral density. It can be also equivalently considered as the total energy spent divided by the total number of bits. So we have both the real dimension and the complex imaginary dimension. So we want to consider this metric in that sense. And the other metric that we are interested in is the user density, which is the number of users per degrees of freedom. So this user density will be with respect to the block length n. And this will represent the total number of users per real degrees of freedom that can simultaneously transmit within the frame resources. Our goal is to be able to understand the relation between these three metrics for different retransmission combining models. So, of course, in this presentation, I only focus on the infinite block length regime. And we recall that the user has a payload of L bits. And normally, the required codebook size for this model is 2 to the L. And when we use the infinite block length regime, what we need to satisfy is the coding rate, capital L divided by N is upper bounded by the capacity of this model. If we use the infinite block length model, the capacity is given by this expression. Also with the additional assumption of the where interference is treated as noise. So this capital C denotes the Shannon capacity, and TIN is simply the assumption of treating interference as noise. And when you want to extend this model to finite block length, from the right-hand side, you need to subtract an expression that depends on the dispersion of the channel, which is also a function of the block length of the model. And that vanishes as the block length goes to infinity. So here I just focus on the infinite block length model. And this will be achievable as n goes to infinity. Of course, for this frame-based model, it is not realistic, but the scaling can be refined by using the finite block length results. And so basically, this result will give us an upper bound on performance because we are assuming that the capacity, the highest possible rate can be achieved. And again, as I mentioned, for the finite block length results, we need to subtract this term from the capacity. I won't go into the details because I assume everybody in this room knows about this. And here, in terms of notation, m as function of the block length and the error is the maximum code size achievable when we want to achieve an error performance by using this code. And some Q function, standard definitions, and channel dispersion V can be written as function of the SINR by treating interference as noise. And C function has been defined previously. So the most basic model is the no multiplexing case, when we do not multiplex transmissions, when we just divide the resources in an orthogonal manner, we can compute the SNR, the spectral efficiency by just computing the received SNR and plugging into the definition of the capacity, where recall that rho was the SNR per user. And here I'm interested in the sum capacity of the model, sum capacity of all the transmitters. And on average, I have capital J divided by T users per transmission. So this is an oversimplification of the model. And for this model, I can compute the EBNOM, the SNR per bit. This ratio can be obtained by dividing the total power spent in transmissions divided by 2 times the spectral efficiency of the model. Again, what I need to do is plug in this expression inside this SNR per bit expression, and in the numerator, I need to consider the total power of the transmissions. So, and then, of course, the sum optimal model cannot be achieved, but when we consider the per user performance, we can also obtain the spectral efficiency and SNR per bit for per individual user. Indeed, these two curves behave interestingly, and they meet at some point when we draw the curves for the spectral efficiency and SNR per bit. I will later show it if the time permits. So this is the standard model that everybody knows without any retransmissions. And then what we have done was to extend this to chase combining with NOMA. We want to allow the user to do capital T retransmissions, and these transmissions are not orthogonal from each other. And recall that orthogonality, non-orthogonality was captured by the eta, which is the inner product of different signature sequences, and rho is the received SNR. So we get under lots of simplifying assumptions, we get a closed form expression under symmetry assumptions. And similarly, we can compute the SNR per bit for this chase combining approach, which is again lower bounded by this expression. And also in the previous talk, you have seen an expression as a lower bound to this energy per bit. And I think that expression in the limit goes to this part, minus 1.59 dB. And these additional terms in this model come from the NOMA and chase combining approach. Again, the same idea can be used to be able to compute the performance when we assume TIN and when we compute the per user performance. What you notice here is, like, unlike scaling the received power by T, you see a bunch of T squares. And this comes from combining the retransmissions and doing maximal ratio combining. That's why you get this square terms in this expression. And the details can be found in the long version, but I don't want to go into the details here. And similarly, the energy per SNR per bit can be written down as the ratio of the total power and the spectral efficiency. And here, to be able to evaluate this limit, you just need to use the L'Hopital's rule to understand the limit as the rho goes to 0. The SNR goes to 0. This is a result, it can be considered as a special case of the previous result, where instead of NOMA, we assume OMA, and things get simplified. I just put the expressions for this. This was also a part of previous work, so this current work aims to generalize the previous work. So under OMA, we can achieve a lower spectral efficiency, and it is given by this expression. And again, we can compute the SNR per bit for this approach, for the sum optimal approach. And similarly, we can obtain the same approach for treating interference noise and obtaining the per user performance. How am I doing in terms of time? 10 minutes. Okay. Okay. Thank you. Okay, so chase combining was one approach to combine retransmissions and obtain the best possible SNR for the user to be decoded. Another approach is incremental redundancy, because we do not want to keep retransmitting the same information. Instead, we can retransmit that information that is different from the previously transmitted one. So this is indeed inspired by the successive refinement model devised by Cover et al. And in incremental redundancy, the source generates different puncturing configurations for the same information bits, even though we have the same information bits every time we are transmitting under different channel conditions. And here, different from the chase combining scenario, you see that I denote the transmissions with different colors, which means that they are different transmissions. They obtained using different puncturing configurations. And at the receiver, what we do is, here the receiver's buffer size is the same as, you can consider this to be the same as the total number of transmissions received from the same source. And instead of having those additive transmissions in this chase combining case, now we are just concatenating them. So this implies that this incremental redundancy can only perform good provided that the buffer size in the receiver is sufficiently large. Again, we can obtain a relation between the required buffer size and its performance we want to achieve. So I denote the buffer size by C sub buf. I think I was disconnected from Zoom. Yes, I was disconnected. Or will it reconnect?
Can you connect to Campus Telecom?
So I was on Eduroam.
Yeah, you can switch to Campus Telecom. Okay, the username is.
Thank you.
Simplifique à craquer.
Ouais.
Is there a dot in between? Wait.
Yes, should open it. Check on Zoom, but it's okay.
Did it reconnect?
Should be.
Should I join from browser? What should I do?
Recording is there?
Yeah.
Okay, so just close.
Should I do close?
Just whatever.
Okay, I do close.
But then she should reconnect again. Yeah.
Yeah.
Here.
Reload.
Open.
Okay.
Okay.
Thank
and
you.
Share screen.
Okay, sorry about that. I got disconnected from Zoom. So what the goal here was to understand the required buffer size of the receiver. And here, so exploiting the ideas from successive refinement of information. So which means in incremental redundancy, we need to retransmit capital T times so that we can correctly recover the desired signal. So you can think that at transmission T that is less than T, the received signal will give us only an estimate of the desired signal. There will be some inaccuracy. And we assume that the buffer size scaled by T is indeed giving the rate, which is smaller than the desired rate that is given by the mutual information between what we received and what we ideally receive and what we approximately estimate. And this will be indeed given by, under the infinite block length assumptions, given by this right-hand side expression, where in the numerator, we have the total power of the users as well as the received noise. But in the denominator, here we have this model that to capture the noise that is due to the finite buffer size constraints. As the buffer size becomes sufficiently high, you will see that this noise will vanish. And on the right-hand side, we will achieve the desired performance. But for small buffer sizes, this noise will be high, and the mutual information between this YT for small t will be small. Okay, so quantization noise in incremental redundancy can be extracted from here, and it can be written as function of the parameters of the system. And we also assume that since we are able to decode the signal at the end of capital T transmissions, this quantization noise vanishes at capital T. So as I mentioned, for the incremental redundancy, each transmission provides an addendum to the previous one, and the decoded signal as a result of capital T transmissions will achieve the desired performance. And as we increase the block length and as the buffer size goes to infinity, we can also obtain the initial results that we have for the standard transmission model. So we can see that with the buffer size increasing, this incremental redundancy model will achieve the same spectral efficiency as the classical model without any combination of retransmissions. Yes. And when we have a smaller buffer size, we clearly have a higher energy requirement in the system. And also, when we have a small buffer size, the gap between the spectral efficiency for the classical model and also incremental redundancy will increase as capital T, as the number of retransmissions increases. So this is the final result for the performance of the spectral efficiency performance for incremental redundancy. So here, different from the chase combining, where all the retransmissions are combined and decoded only once, here, as we have done in successive refinement, we can achieve a certain rate when we have one transmission. And then when we obtain the second transmissions, we can put the we can increment the first rate, we can correct the first rate with the additional information. Therefore, every transmission will improve the achievable rate performance of the receiver. And here, again, some additional parameters. The sigma q squared denotes the quantization power for a given time slot for a given total number of T retransmission attempts. And the restrictive assumption in our model is we always assume at the end of capital T transmissions, the user is successful. Because I don't have much time, I can show some simulation results to understand the relation between spectral efficiency and SNR per bit. Here, the x-axis denotes the spectral efficiency. It's the bits that we can achieve, and y-axis is the energy consumption. You can see for various models. So the sum optimal model for classical, it is hidden behind these curves. The high spectral efficiency curve is for the sum optimal model. For the same color, the low spectral efficiency curve is for the TIN, per user performance. Okay, so you can see that here T is 1. I do not allow retransmissions. That's why all the curves are overlapping. But when I consider NOMA-based retransmissions, even if I do not allow retransmissions by exploiting the non-orthogonality of the transmissions, what we can see is the curve for the red curve that denotes the CC NOMA. It can achieve a better spectral efficiency at a lower energy per bit. So that is the main takeaway from this approach. Even for no transmissions, we can achieve a better spectral efficiency versus energy per bit trade-off. And when we increase the number of transmissions, we can see that all these curves shift. We can distinguish now the different approaches that are relying on retransmissions. And still what we can observe is this NOMA-based transmissions can achieve better performance, the red color. And the pink one denotes the incremental redundancy. And its performance also depends on the buffer size. Therefore, I did multiple experiments for varying buffer sizes to understand this trade-off better. And another figures that I want to show is how the user density scales with SNR per bit. We can see from this curve is the main takeaway is that the black curve is what we have for sum optimal case, the classical case. Again, on the left figure, it is hidden behind the purple curve. And on the right figure, you can see that it is the lowest, it provides the lowest user density per SNR. But as you move away from this curve, you see for the incremental redundancy and other chase combining models, you can achieve a better trade-off. There are other curves with different simulation parameters, which I won't discuss. Just to summarize the contributions, we derived some scaling results to provide upper bounds on the spectral efficiency and user density that we can achieve with combining of HARQ transmissions. And what we observe is like the low SNR regime where rho is small is the relevant regime here where we obtain the best scalings. And the spectral efficiency of the sum optimal strategy will improve with NOMA versus OMA, which was also seen in the simulations. And again, what you see was in the previous figures, those curves for TIN and sum optimal curves meet at some point. That meeting point is when SNR is low. And another important observation was the user density is very sensitive to the number of retransmissions. We get the highest gain for low number of transmissions. As the number of transmissions increase more and more, the gains become incremental. Okay, just to put this slide with all the items here, because I don't have enough time, I am happy to answer any questions you might have. Thank you.